Okay, so this is on page 115 of the note spiral, and we're going to work some problems comparing the normal distribution, which following a z, versus the t distribution. All right, to use the t distribution, we need to have this. We need to be working with the standard deviation of the sample, and either the underlying distribution is normal or our sample size must be 30 or greater. Underlying distribution is normal and we have the sample, we use a t. Underlying distribution is not normal, we need to have a sample of size 30 or greater, just like we did with central limit theorem. Once again, the reason we're using a t is because we're working with the standard deviation of the sample. If we have the standard deviation of the population, we get to work with the z and work with the normal. All right, so we're going to sit there and determine which one we use when, make sure that we know, hey, I can use the normal, or here I need to use the t. So a college professor's data about the incoming freshman indicates that the mean of their high school GPA was 3.4. The students are randomly assigned to freshman writing seminars in a group of 25. Assume that GPA of the students follow the normal distribution. Okay, so even though our sample size is not large enough, in this case, n is less than 30, because we are normal, we're safe to use the z, okay, or t, depending on whether or not we're using the standard deviation of the population. Because here we have to have this. Here we're using the standard deviation of the sample. So if I have this, I'm good with central limit theorem. If I have this, I'm also good because the underlying population is normal. What is the probability the mean GPA of the group is less than 3.3 given the standard deviation of the population is known? They're telling me my standard deviation of the population is 0.35. And in this particular case, the mean GPA was 3.4. So they're asking, what's the probability that it was less than 3.3? So we want the probability that x is less than 3.3. And we have a group of size 25. So in this case, I'm working with z equals x bar minus mu sigma divided by the square root of n. This is what I get to work with. And if I'm drawing a picture of this, by the way, this should be a less than symbol, not a greater than, because this is less. Our mean is 3.4, and our standard deviation, and our mean is 3.4 and 3.3, and we want less. And remember, this goes to negative infinity. So I'm going to do a stats test z test. So I'll say that again, stats test z test. And in this particular case, we want the probability that z is less than 3.3 minus 3.4. Standard deviation of the population was 0.35 divided by the square root of 25. So that's what we're looking for. So stat test z test, oh, that happens to be the first one. My mean happened to be 3.4. My standard deviation was 0.35. The x bar that we're checking is 3.3, and my sample is size 25. Now, the way that they set this up on the calculator is confusing, so look at the way you shaded. We shaded to the left, so I need the less than inequality. Oops. And I want to change this color back. This shows up better. And it's prettier. So the probability, and I need to go back and check my answer real quickly, just to make sure that I have this right. Second bar, stat, test, z-test, mean of 3.5. Oh, excuse me, mean of 3.4. That looks good. And I end up getting the probability that z is less than negative 1.4285 equals 0.0765. All right, so there's my negative 1.4 for my z-score, and there's my probability or my p-value 0.0765. All right, so the next thing says, what's the probability the mean GPA of the group is less than 3 given the standard deviation of the sample is 0.35? Whoa, so we changed this. We're now dealing with the standard deviation of the sample. So S equals 0.35. Notice up here, standard deviation of the population is 0.35. Here we have the standard deviation of the sample is 0.35. So once again, I'm still drawing my picture. Turns out they're going to look the same. If I drew them correctly, this one should be fatter and shorter, but otherwise it's going to be centered at 3.4. We're still working with the 3.3. Oh, we're using a 3 this time. Is less than 3. I think I meant to say 3.3. So let's scratch that out and use 3.3. Because that way we can compare directly. So this one to that one. And we're going to be working with a t distribution because it's the standard deviation of the sample. So t distribution has almost exactly the same formula, except now we're using the standard deviation of the sample. So we want the probability that t, not z, is less than not probability t, probability that x bar is less than 3.3, so nothing has changed. But that's going to be the probability that t is less than 3.3 minus 3.4 over 0.35 divided by the square root of the 25. Now, once again, even though my sample size is too small, I get to use it because they told me the underlying population was approximately normal. So we're going to go back to stats, test, and we're going to see t-test. It's like, okay, that's good. T-test, mean is 3.4, standard deviation the x bar is 3.3. Our standard deviation happens to be 0.35. My sample is size 25, and we're shading to the left. So we have the probability that t is less than negative 1.4286 equals 0.0830. And by the way, the degrees of freedom here is 25 minus 1. All right, 25 minus 1 degrees of freedom. All right, so that takes care of that problem. Let's do one other thing with that. Now, I did that with the t-test. I could have gone second vars TCDF. And you do need to know this. This goes to negative infinity, so I can go negative and type in a bunch of 9s. The upper part of my shading happened to be, the upper part of my shading would be negative 1.4286. And my degrees of freedom happens to be 24. Now to use that, I can't use actual values. With the normal, we got to use actual values. With the t, we actually have to convert it to the t distribution if we're going to use TCDF. So in general, it's a little bit easier It's a little bit easier, I think, doing the t-test. All right, so assume that the duration of human pregnancies can be described as a normal model with a mean of 266. So they're telling me the underlying distribution is normal. And because the underlying distribution is normal, I can use either the t or the z or the z, regardless of the sample size. All right, so regardless of the sample size, I can move ahead. So suppose a certain obstetrician is currently providing prenatal care for 60 pregnant women. What's the probability that the mean duration of the pregnancies will be less than 260? So we want the probability that X bar is less than 260 if the standard deviation of the population is 16. So they have now given us the standard deviation of the population. And because they gave the standard deviation of the population, we can work with a Z. So drawing my graph, the mean is 266. We want to know 260, and it says less. So this is negative infinity. So we want the probability that Z is less than 260 minus the 266 over my standard deviation was 16 divided by the square root of, in this case, 60. And I should have written this down, and please always do. That's because I'm using this formula. Z equals X bar minus mu sigma divided by the square root of n. All right, so that's the formula that I'm using. And this is going to yield the probability that Z is less than some value equals something. Now, stats test is probably the easiest way to do this. So stat test, we're working with a Z because they gave us the standard deviation of the population. Press enter. In this case, our mean happened to be 266. Our standard deviation, our standard deviation was 16. My X bar was 260, and my sample size in this case was 60. We're shading to the left, so I want the less than, which I already have selected. I calculate, I end up getting the probability that Z is less than negative 2.9047 equals 0.0018. So the chance of 60 women having an average gestational period of less than 260 days is pretty small, less than 1%. All right. So suppose a certain obstetrician currently providing prenatal care to 60 women. What's the probability that the mean duration of these patients' pregnancies will be less than 260 if the standard deviation of the sample is 16 days? So now they're saying we're using the standard deviation of the sample. So S equals 16. So that drives us to a T distribution. So now we're working with the T, and I should be writing that equation down. T equals X bar minus mu S divided by the square root of N. My graph, which should always be included, is this. My mean, in this particular case, still 266. We want to know whether it's 260, and remember it goes to negative infinity. Our degrees of freedom in this case are going to be 60 minus 1, right? Because it's always n minus 1. So here we go. We want the probability. Our probability statement ends up being the same. X bar is less than 260. And that is the same as the probability that T is less than 260 minus 266 over standard deviation of 16 divided by the square root of 60. Notice the only difference here is the Z and the T, and the reason being is over up here we have the standard deviation of the population. Here we have standard deviation of the sample. So that yields the probability that t is less than some value. So I'm going to go stats test t-test, and I see a mean of 266, the x-bar of 260, standard deviation in this case is still 16, and we shaded it this way because it's less than, and we end up the probability of t is less than negative 2.9047. Hey, look, these have exactly the same z-score versus a t-score, but the probability is a fair amount difference. All right, this is 0.0018 versus 0.0025. So you can see that they're close, they're still fairly small, but it's more likely with the t-distribution. Why? The t-distribution has more area and has more variance in the tail. All right, that will stop this video, and the next one will have to do with more with confidence intervals.